Over to you, Martin.
Thank you very much. So it's a pleasure to be here this morning. My name is Martijn Tideman, responsible for all the product development within TAS, which is a very nice job. And I'm going to talk about training and validating automated driving applications using physics-based sensor simulation. But first, a few words about our company, TAS International. What are we doing? We are connecting simulation and testing. That's the short version. The longer version is that we are supporting the automotive industry in making vehicles safer and smarter by providing softwares and services for developing and validated automated driving and integrated safety systems. So if you take the good old V-cycle as an engineering paradigm, then we support our clients across the V-cycle, all the way from research and concepts via engineering and development through testing and verification, and the final validation, certification, homologation we do as well. We're not alone anymore. As you may have heard, we joined forces with Siemens as of September 1st, so that's pretty recent. And together we're offering a complete development chain for mechanics and electronics, as well as integrated solutions for verification and validation of automated driving systems. And obviously AI and deep learning are key focus points in this. So let's get back to the company mission, simulation and testing, and the connection between the two. So why do we need testing? By the way, these are a couple of screenshots of testing facilities that we have and tests that we do. We need testing to verify and demonstrate that the final product complies to specific requirements and quality standards, sometimes even put down by the legislator. However, the testing is usually done in an emulated environment, so not, let's say, on the real streets, typically a test track or a laboratory. And also you typically test a subset of real-life use cases. So not the 10 billion miles that everybody's talking about, but just a handful of scenarios, right? Simulation is very complementary to this. Simulation offers you the ability to do quick and cost-effective design iterations, and also to validate the product against all the real-life use cases that there are. So indeed, the 10 billions of miles. Moreover, and this was also mentioned by the previous talks, right? It's safe, perfectly reproducible, and cost-effective. So let's zoom in a little bit more on the simulation solutions that TAS offers. We decided not to focus on the complete vehicle, but only on the most important connections between the vehicle and its environment. So being the sensors, and of course the sensors come with a world model, and this is covered by our simulation package pre-scan. The tires, obviously, because the tires are the one and only physical interface between the world and the car. It's a square centimeter of rubber. It's very important. It determines like 30% of the complete dynamic driving behavior of a car. Also in the framework of automated driving, it's very important because your controllers can make decisions about what they want to do, but if the tires can't transfer to the road, then you're done, right? So it's good to have, it's essential to have good tire models. The humans, another, let's say, part of the car's environment, not the external environment, but the internal environment. And in the end, automated driving needs to protect humans and, of course, transport them safely from A to B. So we do provide active human models consisting of bones, muscles, reflexes that we put in virtual automated cars in pre-scan to test if certain steering or braking maneuvers have an influence on their comfort level, but also if it leads to a crash, what their exact out of position was, so that we can take that into account in the crash simulation, right? Especially if you have fully level 5 automated cars where the humans are turned 90 degrees drinking a cup of coffee. You really want to know what happens with them in emergency situations, including airbag deployment. Well, pre-scan, by the way, is also used for V2V, V2I, V2X modeling. So that comes with the world and sensors. So from now on out, I'm going to focus my talk really on the pre-scan simulation platform for the world and sensor simulation. Just a few items here. So the standard workflow that's been around for 10 years now. First release was in 2007. As a user, you go through a workflow of building a scenario, modeling your sensors, adding your logic, your controller, and running the experiment. Today, that's still possible if you have it pre-scanned installed on a desktop or laptop. But today, we're also running on high-performance clusters and all kinds of hardware-in-the-loop simulations, where this is automated for the large part. These are really the USPs that we're known of. So very easy world modeling, scenario creation, scenario import, very user-friendly. An extensive sensor model library consisting of all the relevant sensors that are today present on automated vehicles, like camera, radar, LiDAR, ultrasound, infrared, V2X, GPS. And last but not least, interfaces with third-party solutions. So for example, the two companies that presented before me, IPG and VI-Grade, they offer excellent vehicle dynamics models with which we interface. Then we offer for each of the sensor technologies, so camera, radar, LiDAR, etc., various levels of sensor models. So very fast, more simple ones or stochastic ones, or very detailed ones that run perhaps a little bit slower, right? So depending on the needs of our user for a specific application, he can choose one of these models on that curve. And these are just some movies that illustrate application areas of pre-scan. So you see an adaptive cruise control in the top left with here a stochastic radar model. You see a pedestrian emergency braking system based on camera radar fusion. And in this scenario, you change weather and light conditions and see what the effects are on the impact speed, given the specific control logic. On the left bottom, you see lane keeping assistance based on a mono camera. And then you see here the parking assistance based on ultrasound. So these are just some snapshots of application areas. Okay, now we have this application area of deep learning, which is rapidly gaining momentum. First, I want to share a few, let's say, personal observations. So, deep learning is increasingly being applied for development of ADAS and highly automated driving, HAD. Almost all big OEMs tiers seem to have established dedicated teams for deep learning. So I just took some of the logos that I saw at a conference which I attended. So these are the companies that presented about deep learning. It's not a complete list, but it just gives you an impression. It is also widely recognized that simulation is necessary to train ADAS and HAD algorithms, especially for the so-called corner cases, so the critical situations with low probability, also known if you have the long tail distributions, so known as the long tails of the long tail distributions, right? And what I also see is that deep learning is mainly currently applied on camera data. At least that's the impression I get. But at the same time, there are some first attempts to also apply it on radar data and LiDAR data, including raw sensor data fusion. I'll talk a little bit more about that later. Okay, so if you want to successfully apply deep learning in the field of automated driving, what do you need? Well, first of all, lots of training data. So again, radar, camera, LiDAR, etc. Secondly, you need so-called ground truth data, the labels or the tags. And thirdly, you need to make sure that you have a certain test coverage and a methodology and environment for the final validation certification, so that you're actually allowed to deploy it on the road. Well, start with the first, in red, a challenge. There's lots of real-world data, obviously, about high probability cases, but insufficient real-world data about low probability critical situations, the corner cases that I talked about. In green, a potential solution, simulation, can of course provide very easily all kinds of very low probability scenarios. About the second, there's a challenge here. If you want to manually tag or label real-world data, that's expensive and also very boring, even if you outsource it to low-wage countries. And here in green, a potential solution, simulation solving this problem by providing kind of a free ground truth segmented image signal with every simulation you run. Well, for the third, I start with a green observation, an opportunity, and because we have high performance computers these days, so we can indeed run lots of scenarios overnight or in the weekend or whatever. for validation purposes. However, there's still an open question, and it's not red, but it's orange, because this question has not been answered yet. The question is, are we able to develop a virtual homologation methodology and environment? Well, let me start with the first one, go a little bit more into depth there. So obviously, Prescan is designed to basically produce synthetic sensor data of a very, very high quality, physics-based, physically correct. So these are just two examples of our physics-based camera, one during nighttime driving and one during a typical tunnel entrance-exit scenario where you see the saturation being adjusted. So the physics-based camera offers full spectrum world simulation, including non-visual wavelength, such as infrared. That's on the left, that's our world model. And then attached to that, there's the sensor model, the sensor and optics, consisting of a lens, filters, imagers. So those two models go hand in hand, always, in Prescan. And in the end, that outputs an image which you can feed to, well, your algorithms. Don't project it on a screen, because then you lose all the fidelity, because the image is reduced to RGB, what the screen emits. Inject it into an ECU. This is our newest radar model. I'm very proud to announce it. This hasn't been shown before. This is a fully ray trace-based, physics-based radar model. The movie is running 5 times slower, just to give you a very clear image of the virtual range Doppler image that we produce. I'm not a radar expert myself, but we have already showed this to some radar people, and they really fall off of their chair if they see this. So we can produce this. Please note that the field of view of the camera is much smaller than the field of view of the radar. So you see much more width in the radar image here. These are some of the main capabilities of our radar model. So it's multipath simulation up to any number of bounces, multi-static antenna configurations, MIMO, and multiple input, multiple outputs, fully customizable waveforms, so the user can do that. For example, FMCW, fast chirp modulation, physical material properties, so we're talking about the world model, very important, including the polarization effects. We have clutter simulation for the trees and the bushes, usually. Micro Doppler effects, like rotating spokes in the bicycle wheels or even in the car wheels, are incorporated. Interferences with different radar sets, so if you have multiple radars on the road, perhaps of different brands, perhaps of the same, the interference can be investigated. Non-perfect component behavior in the antennas. And finally, last but not least, very important, a configurable trade-off, so by the user, between the fidelity level and the performance level. Then the third big sensor, of course, is the LiDAR. Here's a snapshot of our LiDAR model in Prescan, parameterized here for the Velodyne. So you see the typical point cloud. Of course, we can also parameterize it for the popular solid-state LiDARs that are coming up. Okay, so that was the first item. So let me look at the second item. So the labels, well, this is easy in Prescan. We have the so-called image segmentation sensor, which is a ground truth sensor. You put it on the car in the user interface, just like you put any sensor in the car. And it outputs all these segmented images. There's two types, one based on the object, so each object gets a unique ID, name, color, whatever. And the other one is based on the object type, and this one is most often used by our clients. By the way, this looks like camera images. Well, this is a camera image. Are not camera images. But obviously, you can use these segmented images for your radar and LiDAR data as well, right? They just give the objects. Of course, for the radar LiDAR, you also typically want to know distances, which we can, of course, also output. Here's a small movie showing some capabilities of the segmentation sensor. This is already pretty advanced, where we mix real and virtual. But just to give you an impression how it looks. Okay, so in order to put this all to the test, we ran joint projects, two projects independently of each other. One with DFKI, and that's I have to read, can't remember, the German Research Center for Artificial Intelligence, and one with a specific sub-department within Siemens, who are experts on deep learning. And we really wanted to start with the basics. So the main questions we wanted to address are, are the synthetic images generated by Prescan suitable for deep learning-based classifiers? And what criteria do these images need to comply to? Secondly, the question is, does addition of synthetic images to a set of real images offer any added value? The approach we took, we trained based on convolutional neural networks, CNNs, for two types, image segmentation on the one hand and driving scenario classification on the other hand. So image segmentation is indeed, discern the pedestrian from the trash can, from the car, from the tree. And the driving scenario classification is discern a highway scenario from an urban scenario, from a parking scenario, from a rural road scenario automatically. Different models were trained based on real and synthetic data in various ratios. And the performance of these models was evaluated based on a set of real test images that we didn't include in the training set, using confusion matrices and intersection over union tests. Well, these are some impressions of how these tests look. So on the left you see real camera data captured by an automotive camera, a commercial automotive camera. Here in the middle you see let's say the equivalent pre-scan scenarios. So they're not 100% matching, that's also not necessary, but they have kind of like the same features, the same idea. It's the same traffic environment, the same type of objects in it. And on the right you see the output of our image segmentation sensor from these pre-scan images, which is a signal you get for absolutely free. Here you see some more. This is typical for urban scenarios, so following a car at an intersection, some pedestrians crossing. Here's some weird things happening in the scenario, like a car with a trailer. Here's some roadworks suddenly at the intersection. And finally, some critical things with some bicyclists close by, a scooter. And also some night driving scenarios were taken into account. And here, you don't see a lot, but here on the segmented image, you can clearly see that there's a bicyclist in the scenario. Okay, so some results and findings of these exercises. First of all, we found that if you train based on only synthetic data, so no real data whatsoever, you get models that have some sort of performance, but they're not as good as models based on an equal amount of real images, right? Why? Because there's always, no matter how photorealistic you are, and I think this was confirmed by the previous talk, there's always some little bias that the virtual images have that the real images don't have, right? However, if you add synthetic data to real training data, then the quality of the model increases, if you compare it to using only real data. And also, if you keep adding synthetic data, so more and more, the model becomes even better. But there's one prerequisite, and that's that the synthetic input needs to be balanced against the real data. Well, balance means that you have to be realistic, both on the environment part, but also on the sensor and optics part. So on the environment part, you have to make sure your road model, your sky model, your pedestrian material properties have the correct, properties. But also on the sensor side, so your lens of your specific automotive camera introduces some distortions. Your imager has some noise pattern, right? And you need to replicate this in the virtual images. These are really just first steps of pre-scan in the field of deep learning. This gives us confidence, and we are planning to take many more steps, hopefully with one of you, if there are potential customers in the audience. But in any case, we will continue. So next time you see me on stage, probably we'll have more news. Let's go back to the third question there. So how should a virtual homologation methodology and environment look? Well, we have some initial ideas about that, also because we as a company have a lot of experience with homologation. We test, ADAS systems according to the Euro NCAP standards. We do crash tests for 30 years, so we have some experience. So suppose these are the cars on the real world, right? Like the millions of cars that are currently equipped with radar, cameras, whatever. And suppose they share their data, their raw data, or the interpreted data with some sort of cloud. That can be the Siemens MindSphere cloud, but it can also be some other cloud, of course. And suppose you consolidate this into a, let's say, scenario database, right? Then at some point, when you perform data analysis and you assume that there's some sort of Gaussian distribution, you can say, oh, now I have 90% test coverage, or 95 or 99, doesn't really matter, but you can quantify this because you can look at the long tails. You can say, okay, this is a certain percentage, but the bulk we have, right? So what you want to know is then, what am I missing? And you can basically use pre-scan to fill in the missing long tails. You can do that manually, I guess, but you can also perhaps use AI, a deep learned network, to automatically create these long tail scenarios for you based on the real data that you do have. That, of course, then results in a new, updated, consolidated database, and this could be the basis for a homologation framework which is 100%, let's say, which 100% covers the things that can happen in the real world. Well, one of the elements in such a homologation framework must be hardware-in-the-loop simulation, we believe. And just to give you a preview of this, we have built a pre-scan injection setup based on the Drive PX. Currently only camera data, but the next step will be the radar and LiDAR data as well. You can see it at our booth, by the way. We have it here around the corner, so please come have a look. And yeah, we inject the pre-scan camera images into the Drive PX. Yeah, we have some standard DriveWorks algorithms that do the lane marker detection, the pedestrian detection, the free space detection, and you see pretty nice results there. So these are just some samples of that. Here you have the feature detection, and here the lane marker detection. And my next movie shows the free space detection. Okay, I'm coming to the end of my presentation. So I've told you about all these three things and how we as a company, and more specifically pre-scan as a simulation platform, can cover this. One last slide, an outlook. So what we believe should be the next steps. First of all, as I already said, we're going to not only train based on pre-scan virtual camera data, but also our radar and LiDAR models, which I've shown. Secondly, and that's just a natural consequence of that, we are going to experiment with raw sensor data fusion, and some of our clients are also working on that. Thirdly, we want to use neural networks to, let's say, automatically create new scenarios. So perhaps the long tail distributions that I saw you, but you can also think of more variations in whatever fabric that the pedestrian wears that are not pre-programmed, but that are generated by the neural network. And finally, and this is something we've been doing all along and we will continue, we will keep using the latest high-performance computing and GPU technologies to maximize the amount of virtual miles that you can drive per hour, per day, per week, per month, per year, whatever you need. So we're always making sure that performance is not the bottleneck. So thank you very much. It's a pleasure. Perhaps there's room for one or two questions, I'm not sure. And if you have any more questions, then we can answer today, or you want to have a live demo of the pre-scan Drive PX injection setup, please do visit us, booth E41. Thank you very much.